In this video, I will discuss the organic chemistry questions of IIT JEE 2012 paper 2. In this question, we have to predict the major product H, and we have a ethyl methyl ketone here. Although it is not very clear, I can understand. Let me clarify. This is a cyanide anion which is going to react with this ketone and will form an intermediate G, which will again react with 95% H2SO4 under heating condition. So, it is written here 95% H2SO4 and heat, and we will get H. H is the final product, and we have to predict what is H in this reaction. So, to predict the product, we need to do the mechanism of this reaction. Here I have written in a much more clearer way the ethyl methyl ketone here, and it is reacting with cyanide CN minus. So, CN minus is a nucleophile, and it will attack the electrophilic center, the carbonyl carbon, and will form this compound with a negative charge over the oxygen atom, and we have a cyanide group attached. So, when we will use H2SO4, then two things are going to happen. One is that the oxygen O minus is going to get a proton, it will form a OH. The second thing is that the cyanide, the CN, is going to be hydrolyzed to carboxylic acid. So, these two things are happening here. Next, again, as the H plus is still present, so the OH is going to get another proton and will form a positively charged species here, OH2, and this OH2 will leave as water in the next step, and we will get a double bond here. So, now we are having a alpha beta unsaturated carboxylic acid. Now, if we check our option, we can see that in option A, the structure of the product given in option A is actually matching with our predicted product. So, option A will be the correct answer. In this question, it has been asked that among these four options, which will most readily undergo decarboxylation under mild condition. So, we have to remember that a beta keto acid will decarboxylate at a very faster rate. Beta keto acid means if this is the carboxylic acid, then this is the alpha carbon respect to the carboxylic acid group, and this is the beta carbon which is having the keto group. So, option B, beta keto acid, will decarboxylate at a faster rate, because you can see all the other acids, none of the other acids are kind of beta keto acid. So, here in option C we do not have a keto group, here we have a keto group, but it is in gamma position. So, this is the alpha carbon, this is the beta carbon, and this is the gamma carbon, and in option A it does not have any keto group present. So, beta keto acid is only option B, and it will decarboxylate at a faster rate. But why? The reason is given here. You can see that this hydrogen will form a bond with the keto group. So, the keto group will help in taking or removal of this hydrogen from the carboxylic acid group. So, this keto group is going to take the hydrogen, this single bond will come over here, and this one will move over here. So, this whole process is going to happen, and the transition state will look like this, where it will have 6-membered cyclic structure. Look at this, a 6-member cyclic structure where some bonds are breaking, some new bonds are forming, and this 6-member cyclic structure is very stable. That means the transition state will have less energy. That means the activation energy of this reaction will be less. As a result, this reaction will happen at a very fast rate, and thus you will not need any kind of activation. That means mild condition will be fine. So, too much heat is not necessary for this reaction, because the activation energy of this reaction is pretty less. So, after this transformation, first an enol will form a OH and a double bond, which will undergo a kind of tautomerization to form the keto. So, a CO2 will be removed in this step. In this question, a sequence of reaction has been given. It has been said that I is transformed to J in presence of acetic anhydride and sodium acetate. So, acetic anhydride and sodium acetate transforms I to J. Now, J reacts with H2 in presence of palladium charcoal and thionyl chloride and anhydrous LCl3 to give K. So, some information about J is given here. The molecular formula is C9H8O2 and it gives an effervescence on treatment with sodium bicarbonate and a positive Bayer's test. So, when a compound gives a positive Bayer test, that means it has a double bond, and when we get effervescence in presence of sodium bicarbonate, it is the effervescence of carbon dioxide coming from sodium bicarbonate, and that means the compound has a carboxylic acid group. So, this two property of J is already given in the question. We have to keep in mind that when a compound is reacting with acetic anhydride in presence of sodium acetate, that means it is a Perkin reaction, and the product is also a double bond, have a double bond and a carboxylic acid group. So, this is kind of a confirmation that the reaction is a Perkin reaction. So, in the Perkin reaction, always an alpha beta unsaturated carboxylic acid is formed. So, and this is this alpha beta unsaturated carboxylic acid, and this CHC double bond OH group comes from the acetic anhydride part, and this blue part comes from the aldehyde. So, when the aldehyde reacts with acetic anhydride in presence of sodium acetate, a Perkin reaction takes place and an alpha beta unsaturated carboxylic acid is formed. So, we have to go in this manner. So, among these four options, we can see that only one, that option A, is a carboxaldehyde. Others are either alcohol or alkene or ketone. So, as this is a Perkin reaction, we got the indication from the reagent, that is acetic anhydride and sodium acetate, as well as from the product which has a double bond and a carboxylic acid group. So, from these indication, we are pretty sure that this reaction is a Perkin reaction, and Perkin reaction is a reaction between acetic anhydride and an aldehyde. So, here in option A, we only have the aldehyde. So, it will react in presence of sodium acetate and acetic anhydride to give the product J. The reaction mechanism is given here, where you can see that, let me take the laser pointer. Yeah, here you can see that this is the acetic anhydride. It is reacting with sodium acetate, which is acting as a base and taking a proton from the acetic anhydride. Now, we have the CH2 minus, which is attacking the carboxaldehyde, the benzaldehyde, forming a OH group here, which eventually undergo dehydration to form a double bond, and then again hydrolysis to form a carboxylic acid, alpha beta unsaturated carboxylic acid. Now, in the next step, so we know the structure of J here, this is J of course, and now we need to know the structure of K. So, we know the structure of I, which is option A, we know the structure of the intermediate J, and now we need to know the structure of K. So, what is K? What we are doing actually, we are doing first, we are reacting our J with PDCH2, that means a reduction. This was J and we are doing a reduction, and what we are getting here? We are getting a reduced product, that means the double bond is getting reduced. We have the carboxylic acid here. When we are adding thionyl chloride to it, the OH group of the carboxylic acid is getting converted to the corresponding Cl, that means we are getting acetyl chloride. Now, in presence of the AlCl3, intramolecular FC reaction, that is Friedel-Crafts reaction, is going on here. So, the nearest end, that means the ortho position, is reacting, and this AlCl3 is behaving as a Lewis acid. So, it is accepting the chlorine from here. So, a cyclic intermediate is formed which after deprotonation is giving the actual product K. So this is our K. Now let us check that which among the following option has the same structure as that of our predicted K. If we check, we will get that C has this structure. So C is the answer. So the compound A is C. In this question again, a reaction sequence is given. So we will start from T and then we will go to U and V and W. So the first reaction is a lithium aluminum hydride reduction. So whenever we have an ester, suppose let me start with a very simple ester. So acetic acid, the methyl ester of acetic acid, so OMe. So what will happen if I use some lithium aluminum hydride to it? So we have one OMe group here and a CO group here. So in this reduction, what will happen? We will get CH3 CH2OH as well as MEOH. That means this carbon is getting oxygen, that means a OH group here, not an oxygen but a hydroxide group, and the other carbon, that is Me, is also getting a hydroxide group. So two hydroxide groups are forming from an ester. So we are starting with an ester, and after this reduction in presence of lithium aluminum hydride, we are getting 2 alcohol. So 2 alcohol will form after the reduction of an ester. So here we have a cyclic ester. We can see in the question we have a cyclic ester, this one. So this one is reacting in presence of lithium aluminum hydride. So here also this carbon will get a OH group, so this one, and the other carbon here is also getting an OH group. So 2 alcohol is formed, but it is in the same compound. That means it is not getting away from the compound. The 2 OH group are connected within the compound. Now we are oxidizing it in presence of Cro3. So Cro3 oxidation in presence of protons will oxidize this 2 carbon to carboxylic acid. So this 2 carbon will be converted to carboxylic acid. So this one will be the product. Now in another way, we are also doing a different thing with this compound. So this is U actually. This was the starting compound was T, and this is U, and we did the oxidation and we obtained V here. So in another way, we can take U and use some acetic anhydride. So we have some hydroxide group. So whenever hydroxide group reacts with acetic anhydride, it will form the corresponding ester, the acetate ester. So CH3 C double bond O is going to attach with the OH group. So 2 OH groups are there. So 2 CH3 C double bond O group will attach with the 2 OH group. So diester will form. So this is our W. Okay, so now we have UVW. We have the structure of UVW, and now we will check the option. So option A is saying that T is soluble in hot aqueous sodium hydroxide. So if we use hot aqueous sodium hydroxide, it will be converted, because this is the ester, so there will be a hydrolysis of this ester linkage. So a compound like this will form, where this will be the CH3. So this will be C double bond O, ONA, and the OH. So it will dissociate, the ester linkage will dissociate, and a sodium salt or the corresponding acid will form, and this will be soluble because of this salt formation. So yes, option A is correct. What about option B? U is optically active. So let us check the structure of U. We can see that it is not optically active because the central carbon, this carbon is not chiral, or any other carbon in this system is not chiral, because this is a symmetric molecule. Here you can see this central carbon has 2 CH2OH group in both hands. That means it is symmetric. So option B is not correct. Option C, molecular formula of W is C10H 18O4. So let us count. So how many C we have? 1 C here, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So C10, fine, it is matching till now. C10 H. So how many H we have? So here we have 3 H's, 3 and here 2, 5, 6, 7, here 1, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So H18 matching. Oxygen, how many oxygen we have? We have 1, 2, 3, 4. So total 4 oxygen. So O4. This is also matching. So option C is also correct. What about option D? D gives effervescence on treatment with aqueous sodium bicarbonate. We know that when there will be a carboxylic acid group, it will react with sodium bicarbonate to give effervescence. Now let us check if V has a carboxylic acid group. Yes, it has 2 carboxylic acid groups, so definitely it is going to give effervescence in presence of sodium bicarbonate. So option D is also correct. So option A, C and D are correct. In this question, we have to check the following structure and we have to decide that which among the following options are correct. It may happen that more than one options are also correct. So one by one we have to check all the options. So let us check option A, where M and N are non-mirror image stereoisomers. So let us draw M and N again here. So this is the single bond connecting the 2 carbon atom. So we have these 3 different group at one end. This is M, and we also have H here, CH3 OH. So this one is CH. We have to make it a little bit long bond so it will be easily visible. Yes. So this one is M, and now let me take the OH as it is drawn here. So I am not doing any change. I am just taking as it is drawn here in the question. So H, Cl, CH3. So to compare, what I will do now, I will rotate N along this single bond. So I will just rotate this. I will rotate this single bond at a perpendicular, around a perpendicular axis. I will rotate it along this axis to 180 degree. So what will happen now? This carbon will come to the front and this one will go at this side. So the resulting structure will look like this. So this OH will come over here and this H will come here, and the Cl which was there will come down here, and this H will come here, and this OH will come here, and the CH3 below. Now let us compare the structure of M and N. So H, this carbon, the configuration of this carbon and this carbon are mirror image of one another. But if we check the red carbon, that means this one and this one, we can see that they are not mirror image of one another. So M and N are non-mirror image stereoisomers. So overall they are non-mirror image. So if I put a mirror here, so this one M is not an image of N. So M and N are not mirror image stereoisomers. So they are kind of diastereomer. So option A is actually a correct option. Now M and O are identical. So to prove that, I have to draw O here. So let me erase this part. I will keep the M Okay, now let me draw the O here. So this is the O. So we have Cl in this position, H here, OH here, here H, CH3, OH, and this will be Cl. So now what I will do to get a proper orientation so that I can compare M and O, I will rotate the single bond. So I will rotate around this single bond 180 degree again. So what is going to happen? The structure will change. So this portion will remain as it is. I'm not doing anything here. The other portion, that is the other carbon, the orientation of the groups will change. So this Cl, which was at the top, will come down because I have rotated it 180 degrees. So this OH will come here, and this H will come here. Now let us compare M and O. So this is basically O. So I will compare M with O. Here I can see that this carbon, that is, let me number this carbon. This is carbon 1 and this is carbon 2. So carbon 1 here have the same orientation of the carbon 1 of M. So M and O have the same orientation at carbon 1. What about carbon 2? Yes, if we compare carbon 2, then we'll get that yes, in carbon 2 also M and O both have the same orientation. That means option B is correct, that M and O are identical. What about C, that is M and P are enantiomers? Let me check. So I already have the structure of M. I will draw the structure of P in Shaw-Horst projection, because here it is in Newman projection. Comparing to different projections is quite difficult. So what I will do, I will draw P in in Shaw-Horst projection. Just a moment. So M is already there. Let me draw P in Shaw-Horst projection. So the single bond connecting the two carbons, then the carbon which is near to us, CH3, at top, OH at left hand side, and hydrogen at right hand side, and the carbon which is far away from us, OH at right hand side, H at left hand side, and Cl below. So we have this one. So now to compare, so the question means the option says that M and P are enantiomers. That means they will be mirror image of one another. So we can see that carbon 2 is already the mirror image. To check about carbon 1, we have to reorient it. That means we have to rotate along this single bond, which is allowed. So I will rotate it at 180 degree centigrade, 180 degree angle. So here we have the new positions. So CH3 will come down after the rotation. This H is going to come here, and this OH is going to come here. So now this is the new P, or the old P in a new way. Now we can compare M and P. If we check, we will see that yes, this is the mirror image, because these two H are near, these two OH are far. Similarly, these two H are near and these two OH are far. And also, sorry, I have made a mistake while drawing. This will be the Cl here. So this one will be the Cl. So this is also mirror image, and this CH3 is also mirror image. So that means option C is correct. M and P are enantiomers. They are mirror image of one another, and they are non-superimposable mirror image. That means they are enantiomers. So now the last option, that is M and Q are identical. How to prove that? To prove that, we have to draw Q again in Shaw-Horst projection. So let me erase this P and I will draw Q here in Shaw-Horst projection. So here, so first let me draw the carbon which is away from us. So OH at left hand side, H at right hand side, and Cl below. The neocarbon have CH3 at top, OH at left hand side, H at right hand side. So now to compare again, we need to rotate this single bond at 180 degree. That means H, OH, Cl. So this is carbon 2, and after rotation the CH3 here will come down, the H, this H will come here, and this OH will come here. Yes, now let us check. M and Q are identical. Are they identical? So we can see that carbon 2 of M and Q are identical, but what about carbon 1? No, carbon 1 is not identical, so it's different. So option D is not correct. If you have liked my video, please click the thumbs up button as well as share the link with other people. And for more videos, please subscribe my channel and press the bell icon. Most importantly, please comment below about your needs related to chemistry so that I can make more videos on several other topics.